Recorded as rolling. It is Friday, August 26th. We have a short day, so we're gonna make the most of it. Oh, remind you guys, by the next time I see you, there will have been a rocket launch to the moon, but not much before I see you next 8:33 in the morning on Monday. So put it in your planner. You guys are using those planners. Oh yeah. Rocket launch to the moon. 8:33 in the morning. So probably like as you guys are walking on campus, right, look to the north. All right, so you guys have learned a lot about linear motion this week. You guys did lab, we did lots of graphs. I introduced you guys to those three kinematic equations, and you guys use these to solve a bunch of problems. And we did get a start on these college physics problems. So these college physics problems, remember, I'm picking up a week from now. There's also been that AP Classroom progress check open, so take a look at that. Gonna go over that not this coming Tuesday, but the one after. All right, so those things are all going around. Now, on the back of this page are 20 conceptual questions, and we are about to right now do a Kahoot on those questions. So if you wanted to follow along and like circle the right answers, this is not a page you're going to pick up from you guys, but might help you out. If you have a really good core understanding of how linear motion works, then I think you will do quite fine on these conceptual questions. Almost everybody's hopped on here, which is super awesome. Thank you guys for hopping on right before I start the recording. So they can get to our time. All right, so when I hit start, if it's like it was last year, then that 6-digit pin should be at the bottom of the screen. Here's your just about to hop on. So here we go. One possible unit of speed is oh yeah, all of the above might be the answer. Yeah, in this case it is. Those are all true. Since we're Americans, we're obviously familiar with miles per hour, but kilometers per hour you oftentimes use highway traffic in other countries. Even light years per century checks out, because look, if you guys got some kind of distance per unit time, distance per time, anything in distance per time can describe a speed or a velocity, right? And in this class, most often we'll use meters per second. Your guys' speed sensors the other day were using meters per second. An object moves 5 meters in the first second, 5 meters in the next second, 5 meters in the third second. What is the acceleration? Oh, pretty good. Most got that. Yeah, it'd be 0 meters per second squared. Right. Let me ask you guys a different question. What is the velocity? The velocity is 5 meters per second, but acceleration is a rate change of velocity. You guys see there's no rate change of velocity? You guys remember 0 acceleration and constant velocity. Are those synonyms? 0 acceleration, constant velocity? Yeah, that's the same thing, which is, there's an example of it right there. We got Scarlett, Nick, Braden, Matt, Marcus. Some of you guys are beating math. As an object falls freely in a vacuum, what is increasing? It is velocity. So isn't it like picking up speed? You guys remember we did a few examples of like some version of dropping a ball off a cliff, right? Then it had you guys like throwing it one or another, but drop a ball off a cliff, or even your guys' Hot Wheels lab, you're rolling those cars down. That was a slowed down version of dropping a ball off a cliff, right? So anything you drop, okay, it's gonna fall faster, faster, faster. Do you guys remember what is the free fall gravity rate on Earth? 9.8 meters per second. Yeah, 9.8 meters per second squared, or 10 meters per second squared. More often than not, I'll probably round to 10 meters per second squared. AP does the same thing. That means that every second it picks up another 10 meters per second. It picks up 10 meters per second per passing second. That's called 10 meters per second squared. So the velocity is increasing by that much. But what is acceleration? Guys, if acceleration is not increasing, what is acceleration in that scenario? Constant, right? Right. And notice too, it says in a vacuum. Are we ignoring air drag in this class? Yeah, we're ignoring air drag. If you put in air drag, I've seen that solved, I think, once before in my life, and it was in a post calculus 3 class. So yeah, save that for then. Ooh, Scarlet leading the pack. A ball is thrown straight upward and is caught when it comes back down. In the absence of air resistance, its speed when caught. All right, who's got that? Same as when it had been thrown upwards. This one I want to draw. It's hang tight. Let's switch over real fast. There was a question I asked you guys yesterday. I said if you throw a ball straight upwards at 30 meters per second, here's the ground. How high is that ball going to go? So let's do this. 30 meters per second. Okay. So let's go back to that story, but look at this from a different point of view. Instead, you guys tell me, how fast is that ball going after 1 second? How many guys were taking about 20 meters per second? How did I know it was 20 meters per second? Because as long as you're on Earth, you guys see the velocity change by 10 meters per second during that 1 second towards the Earth. In fact, if you guys really want an equation with that, wouldn't it go like this? Final velocity equals initial velocity plus acceleration times time. Right here, let's pop some numbers. So this number was 30 meters per second. And then after 1 second, now if you throw it upwards and call upwards positive, then gravity's pulling which way? Down, which is called negative. We'll call that negative 10 meters per second squared. You guys see 30 minus 10 is just 20. Then how about another second goes by and I take a picture again? Now what's the speed? Now it's down to only 10 meters per second. Maybe you have like a slight time axis going to the right, like frame by frame. How about another second? How fast is it going? 0 meters per second. So 0 meters per second here. Right. Now maybe the ball's going like pretty straight up it and kind of a time axis, right? Kind of spreading out to it. Hey, look at, do you guys see how like the ball's getting like closer and closer together every 6 a second? In fact, what shape curve do you think this is making? A parabola, kind of upside down parabola here. So it's like a time axis here. Okay. How about another second? How fast is the ball going? 10 meters per second. Yeah, 10 meters per second, but downward. Okay. Yeah, you could say negative, or you could do a directional vector and then point it in that direction. Also, what I'm trying to do is make these directions kind of proportional. See how this is like 3 units long, this is like 2 units long, this is like 1 unit long, this is 1 unit long. This next one's going to be like 2 units long for 20 meters per second down. And right numerically it would be negative 20. But, okay. And then by the time it reaches ground level again, you're up to 30 meters per second is the speed, or you could say negative 30 meters per second is the velocity. Okay. Now look at that. Do you guys see how every elevation, it's equal speeds, just opposite directions? So the peak at 10, or sorry, the peak at 0, I should say. Always 0 at the top. 10, 20, 30 meters per second. Okay. See if you guys remember this from yesterday. For this exact scenario, which I threw to you guys yesterday, it's a different way of looking at it. How high did this ball go? What's its max height? The answers are in your notes from yesterday. Here, let's figure it out. Which of those 3 equations do you think is going to solve this for you? The third one? We did use the third one yesterday, didn't we? And we go final velocity squared equals initial velocity squared plus 2ax. Right? Now, if I'm asking the question, how high does the ball go? Which of these variables are we solving for? Like x. Right? Now, sometimes actually you could replace with h in this case for height, or sometimes you see a y. That a acceleration, in this context, it could be lowercase g for like Earth gravity. That's some reason with that. Okay. Let's say one of these v's is going to be 0, and the other is going to be 30, right? So depending on your perspective, let's do what we did yesterday. It's 0 at the top, meters per second, equals you threw it at 30 meters per second, plus 2 times gravity's pulling at negative 10 meters per second squared, times x to represent the maximum height, you know it's maximum height because that would align with 0 meters per second final velocity. Okay. Subtract 30, divide by 20. Or sorry, whoops, I missed something. What did I miss? Square. 30 squared is 900. Subtract it over, divide by 20. You get 45 meters. Goes up 45 meters to the top. You know what? I want to poke around a little bit, see if another equation works. What about this? X equals v naught t plus 1/2 at squared. Let's see if this could also answer the question. Because, guys, how many seconds would it take for the ball to reach the top? 3 seconds. You guys see 3 seconds? Right? Okay, so let's just pop in 3 seconds. So I threw this thing at 30 meters per second. It's going up 3 seconds. Plus 1/2. Gravity's pulling down 10 meters per second squared. 3 seconds. Don't forget to square this 3. Let's see what this is. This is 90 meters plus 3 squared is 9 times 10 divided by 2, and it's negative 45 meters, which is 45 meters. Same thing, just a different way of getting there. Right? There's lots of trips through the lots of different trails through the forest to the same destination. Yeah, so if you throw it up at 30 meters per second, it's going to rise to a maximum height of 45 meters. Okay. Or if you somehow measure the height, goes up to 45 meters, you know, therefore you had to have thrown it at 30 meters per second. Ah, yeah. Let's switch back to Kahoot. Back to Kahoot. All right. Scarlett, still in the lead. Brayden, Alex, Elijah, and Jackson. A ball thrown upward rises and falls back to the floor. During this time, acceleration is always. Yeah, guys, which way does gravity pull? Always down, and that would also represent the direction of acceleration for anything in free fall, right? It's always down. Okay. What about switch over just for real fast? Okay, if you're watching the video, you can see the thumbnail version of this. Okay. Guys, when the ball is headed up, its velocity is which way? Up. The acceleration is which way? Down. So is it speeding up or slowing down? Slowing down. Okay, now it reaches the peak and it's going to start falling back down. Its velocity is which way? Down. Acceleration is which way? Down. Is it speeding up or slowing down? Now it's speeding up. Oh, right. So velocity and acceleration have the same direction. It's speeding up. If they have opposite directions, it's slow down. Right? You guys remember that from earlier this week? This is a pretty good review, right? We got Scarlett still in the lead. Brayden's on fire. Elijah, Nick, and Rob coming up. Suppose you travel 300 kilometers, takes you 5 hours. What's your 5 hours? What's your average speed? 300 kilometers in 5 hours. Yeah. Oh, look at that. Perfect. Everybody got it. 60 kilometers per hour. So you did displacement over time. Right. Now, notice it says average speed there, right? Guys, do you see average speed very often in this class? Hardly ever. That's like total displacement over total time. Those 3 kinematic equations up there on that green poster, those all refer to instantaneous values, right? Okay. Like, well, the velocities are instantaneous. Okay. All right. So same leaders. Ball thrown straight upward at the top of its path. Its instantaneous speed is. Yeah, 0 meters per second, right? So at the maximum height, there's 0 meters per second for anything thrown straight up. Who has a question on that? You guys get that? All right. Ooh, Brayden on fire again. Scarlett's still in the lead. Ball's thrown straight upward at the top of its path. Its acceleration is. Yeah, about 10 meters per second squared downwards, right? Guys, anything in free fall, suppose it's moving up, suppose it's moving down, suppose it's at the top of this path. Suppose you throw it sideways. We haven't quite gotten to that yet, but suppose you did throw something sideways. Which way is gravity pulling for anything in free fall? Down, and it's pulling it at a rate of 10 meters per second squared, right? Yeah. Ah, Braden finally taking top spot. Car accelerates at 3 meters per second squared. How much time to reach 15 meters per second?
Purple guys.
There you go. 5 seconds. That's almost everybody got that. Just in case you did. Here, you guys see this green poster? Take a look at that second equation. So final velocity equals initial velocity plus AT. Now, if you start from rest, which is, I guess it's implied in the question. So let's say v naught 0, right? Meters per second. So if you speed up at 3 meters per second, and you do that for 5 seconds, wouldn't that bring you up to 50 meters per second? Okay, you guys see that speedometer needle moving on there? Right. Okay. 3 times 5 is 15. Oh yeah. Right in the top spot. A freely falling object starts from rest. After falling for 5 seconds, its speed will be about. Yeah. All right. 50 meters per second. This was drop a ball at the edge of the cliff. This is in your notes, but you guys got that. All right. So, or you can chop that second equation again. So 10 meters per second squared times 5 seconds brings you up to 50 meters per second. Okay. Right. Remember, every second it picks up another 10 meters per second. 10, 20, 30, 40, 50. Boom, 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 boom. Who has any question? Any question? All right. I got Braden, Elijah, Rick, Scarlett, Rob. When you look at the speedometer of a moving car, you see that car's what? Yeah, instantaneous speed. The speedometer tells you the speed of the car at that instant. Right? At that instant. Any question why it's that, not anything else? Move on. Braden, keeping the lead. Car starts from rest. After 5 seconds is moving 30 meters per second. What was the acceleration? Yeah, 6 meters per second squared. You say 6 times 5 is 30, right? So 6 meters per second squared, do that for 5 seconds, brings you up to 30 meters per second. That's also the second equation on that green poster, right? Second equation. Vf equals v naught plus at. Guys good? All good? Scarlet on fire. Alex jumping in the top 5. Braden still in the lead. In a vacuum, objects fall at constant. Constant acceleration, right? Right. And on Earth, what is that value equal to? Okay, so 9.8 meters per second, which is called 9.8 meters per second squared. Yeah, and that's more often than not, we'll round that to about 10 meters per second squared. All right. Drops of water fall from a leaky faucet. All right. Yeah, most of you guys got that. Let's switch the screen over here because I've actually got a picture that sort of gives away the answer. You guys remember this from a few minutes back? Okay. Does this look kind of like water drops from a leaky faucet? Well, okay, not quite. Here, how about this? Which looks more realistic? Let's get some faucets going. Okay. Suppose you're looking at some animation. Which I'll throw in a third one. Okay, three faucets here. So you see, which one looks the most realistic? The left, middle, or right one? Which one's the most realistic?
The right one.
One on the right. Yeah. That's what you see. Yeah. Try it at home. See it yourself. One on the right. All right, back over to Kahoot. Great, keeps the lead. 10 seconds. Scarlet moving up. Bob, jump off the ground with twice the jumping speed of Alan. Just after his feet had left the floor. Yeah, same acceleration. Everybody had, once your feet have left the floor, you're in free fall. If you're in free fall, your downward acceleration is 10 meters per second squared. There you go. Hey, I have my own follow-up question. So Bob can jump with twice the speed, right? A different story you can attach to the same idea is, suppose you can throw a ball twice as fast, and you and your friends get together and you're saying, you can throw the ball the highest, and you can throw twice as fast as your friend, right? So, same idea, right? How much higher can Bob jump compared to Alan? Suppose Alan jumps off the floor like 100 centimeters. How far does Bob jump? And it's not 200 centimeters. If you can jump with twice the speed, huh? No, you would go higher. Or how about this? If you're throwing a ball, because you can throw it twice as fast. Ooh, good guess. You have the right idea. Huh? Oh, ooh, I'm gonna switch my screen over. Check this out.
I guess I did it wrong.
Let's see. If you have throwing speed, you're interested in height. Which of those three equations looks good to answer that? First, second, or third? I think the third will answer it the fastest, right? Not the only way through the force, but it's one way. So we have some version of this going on, right? Okay. Now, maximal height, wouldn't one of these be 0? Right. You know what? I'm gonna do a little trick here. I'm gonna fudge some things. Because well, here, this is a little trick. It's gonna be kind of wrong. It's like how like 2 wrongs to make a right, or I don't know, maybe it's the opposite. Don't learn your morals from me, I guess. Okay? So if I just let one of these go to 0 and just keep all my numbers positive, it's like the relationship is here. Now I think some of you guys are on the fact that there's some kind of squared relationship going on between this guy and this guy. But if you said it's a factor of 4, then I think you got the squared relationship the opposite way. Okay. So suppose you can throw it twice as fast, right? So if you double the speed, so you guys see the speed goes up by a factor of 2, right? So 2a instead of let's say Alan and Bob, right? Let's say this is the speed of Alan, and then this is the speed of Bob, which is like twice that of Alan, right? So 2 times the speed of Alan, right? So this would be the height that Alan reaches, a, right? And then x for Bob, right? Now what is x for Bob compared to x of Alan? Right? Oh, did I tell you guys something wrong?
No.
Hold on. Try. Oh, you know what? You said 400. You said 4 times, right? Yeah, you're right. You're right. It is 4 times. Right? It is 4 times because that factor 2 gets squared, so it's 4 times. You get 4 times over here. You're right. It would be 4 times. Okay. Let me do this in terms of variables, and we'll look at this a different way. You could also solve for this x. Here, let me go back to the original statement. Df equals v squared equals v naught squared plus 2ax. Okay, and then guys, I know one of these is 0. Solve for v. Okay. Couldn't v be equal to square root 2ax, right? Or sometimes square root 2gh if you like drop something from rest. If you here, you guys remember Galileo's experiment? Drop a ball, how fast is it crash landing on the ground? And it's always this expression. It's always square root 2gh if you know the height of the cliff. Right. Right. So if your throwing speed is twice as much, do you guys see how it's going to go to 4 times the height? Yes. So you guys are right. It is 4 times the height. Okay. So or think of it the other way. If you throw a ball to 4 times the height, or if you jump to 4 times the height, what's a factor of 4 being square rooted? Yeah, twice the speed. So if I had a cliff that was 4 times as tall, it would crash land on the ground with twice the speed of the original cliff. Okay. So yeah, if you can jump twice as fast, or if you can throw a ball twice as fast, it will go 4 times the height. There you go, 4 times. All right, but everybody has the same acceleration. Was the Kahoot question? All right. Next one. Ooh, Ronald McDonald getting in the books. Braden's still in the lead. Oh, okay. What's the value of G at Earth's surface? Uh, 10 meters per second squared. All right, next. Ball is dropped off a cliff. Each second, its speed increases by how much? Ten meters per second. Oh yeah, right. 10 meters per second per passing second. You drop a feather and a coin, which in a vacuum chamber, which reaches the ground first. Vacuum chamber. Yeah, they tie because everything falls at the same rate. Projectiles fired straight up at 30 meters per second. The total time to return to the ground. Six seconds. Right, let me show you guys a couple perspectives of why the answer is 6 seconds. Okay. Hey, we did this earlier. Throw it up at 30 meters per second. Tick, 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 tick. You guys see 6 seconds? Right? Do you think you also could have done V final equals V initial plus AT? Let's try it out. I got negative 30 meters per second equals positive 30 meters per second plus negative 10 meters per second squared times some amount t. Subtract over 30, negative 60 meters per second equals negative 10 meters per second squared t. You guys see t is going to be positive 6 seconds. Okay, there it is with the equations. So there you go, a couple perspectives. All right, you're getting this. And finally, last one for the win. Suppose the jumper claims a hang time of 6 seconds, which would be crazy. But if that was true, how high would he be able to jump? Okay, claims a hang time of 6 seconds. That's from the floor back to the floor. How many seconds up is that? 3. Isn't it 3 seconds up, 3 seconds down? Hey, is the answer on this paper I've just been drawing over and over? 3 seconds up, 3 seconds down. Huh. In fact, if you just look at the second half of that, if you drop a ball from the edge of a cliff, how far does it fall in 3 seconds? Because that also answers the question, right? Right? You guys get that? Right, so multiple perspectives, they should all lead to the same answer, right?
I don't know.
Okay, 45 meters. Let's see who won this, and then I'll go back and take another look at that. With the bronze, Scarlet. With the silver, Braden. And the gold goes to Elijah. Oh yeah, Kahoot winners. All right, all right. Oh, good. Okay. So yeah, that very last question was if your hang time is 6 seconds, 3 seconds up, 3 seconds down. How high can you actually jump to? So well, we solved that already with this right here, right? 45 meters, 45 meters. That's one way to do it. Man. Okay, I really wish we had 5 more minutes, but here's the next activity I was going to do, just to have you guys think about this going to the weekend. You guys see those rulers on your desk? You guys see those rulers? Right. I was going to have you guys, we'll probably do this next week, do a reaction time activity, which goes like this. You partner up with a friend. I had you groups today too. Right? And your friend holds a ruler out. Then you, because we're testing your reaction time, hold your hand right at the 0 centimeter mark, right? Like right down here at 0 centimeters, and then your friend is going to drop the ruler and you catch it as fast as you can. Now, is that ruler accelerating as it's falling? Yeah, at 10 meters per second squared, right? Or 9.8, really like, right? Do you think you could use the fact of how far the ruler is falling to figure out what your reaction time is? Is that going to be some version of x equals 1/2 a t squared? If you solve for reaction time, times 2 divided by g, take the square root, would time be 2 times the falling distance divided by Earth gravity, take the square root. Okay. Now for x, plug in the number of meters. For example, suppose you catch it at 12 centimeters. How many meters is that? All right, you can do something like this. All right, you guys have a great weekend, and we'll continue physics adventure on Monday. You guys can catch the rocket launch on Monday.